Polarization is a phenomenon associated with light waves but not with sound waves. State what is meant, what is the meaning of polarization? I'll just read through. Oscillations, polarization means oscillations are in a single direction, perpendicular to the direction of propagation. What do we mean direction of propagation? Direction of propagation, that's the direction that the energy is traveling, or that the direction of the wave. That's the direction of the wave, direction of the energy. So of course, why are we insisting on perpendicular to the direction of propagation? We are just emphasizing that actually it happens in transverse waves. But in the real sense, the most important part is only this part here, that oscillations are in a single direction. So you can exchange the word oscillations with vibrations. We could say vibrations are in a single direction. We can also say that vibrations are in a single plane. That's all a polarization. So polarization, it means that where vibrations of a wave is polarized if we know that its vibrations are in a single plane. Then a wave is polarized. So that's it. Of course, here going further to say now perpendicular to the direction of propagation of the wave is to emphasize that this happens in a stationary wave. Because of course, in a longitudinal wave, there are also vibrations in a longitudinal wave. But vibrations in a longitudinal wave are not very important, the vibrations in a longitudinal wave, because those ones are parallel to the direction of propagation of the wave. So those ones, they are not in several directions. They are in one direction, parallel to the direction of propagation of the wave. Unlike those ones which are perpendicular to the direction of propagation of the wave, that can be in several different planes. So that's why we remove all other planes and we're left with one direction, and then we say that this wave is plane polarized, or it's polarized in one plane. State why light waves can be polarized, but sound waves cannot. As I have already said, light waves are transverse and sound waves are longitudinal. So for that also reason, longitudinal waves do not have several directions, different directions. They just have one direction. Polarization is all about removing oscillations in all several directions to be left with oscillations in only one direction or one plane. So since longitudinal waves like sound are already in one direction only, it means that there is no purpose or room to remove vibrations in all directions. There's only one direction anyway. But light waves now are transverse waves. Transverse waves have vibrations in several directions, so we can remove vibrations in several directions from the wave and leave vibrations in one direction. So that's why light waves can be polarized. Two polarizing filters, A and B, are positioned so that their planes are parallel to each other. So to see that their planes are parallel to each other, we check the transmission axis like that. Check this transmission axis. The other one is said to be horizontal. The other one is said to be vertical. So their planes are parallel to each other. The plane of this polarizing filter. Number one, they are parallel to each other. And then they are perpendicular. Sorry, I may have to restart on this part here. When we say that they are parallel to each other, I interpreted it wrong. They are parallel to each other because both of them, this one is, you can see this plane and this plane, they are one after the other. They are parallel, meaning that their planes will never intersect even if we try to move in any direction. If we draw a line parallel to this plane, it would never meet with a line parallel to this plane. This line parallel to this plane will go like that, and the line parallel to this plane will go like that. They would never meet because they are coming from planes that are parallel to each other. Then these planes, they are also perpendicular to the central line, XY. Okay, so meaning that this one is making an angle of 90 degrees with this part here. So is this one also making an angle of 90 degrees with this central transmission axis. Okay, the transmission axis of filter A is vertical and the transmission axis of filter B is horizontal. So that much part is clear. This is horizontal, this is vertical. Unpolarized light, so we have unpolarized light coming here, light which is coming and entering through the first filter, filter A. Unpolarized light of single frequency is directed along the line XY, so it is incident towards filter A along the line XY from a source positioned at X. The light emerging from filter A is vertically plane polarized and has intensity I naught. So when that light emerges here, it's now vertically plane polarized. When it entered, it was unpolarized. Exiting, it is polarized, vertically plane polarized. Why is it like that? It is like that because the transmission axis here is vertical. So any light that enters through this, when it enters through this filter, which has got a transmission axis which is vertical, when it exits from the other side, it will exit vertically plane polarized. Okay? Okay, so filter B is rotated from its starting position. So filter B, this one now, it's rotated from its starting position about the line XY as shown in fig 4.1. So its starting position there. After rotation, the intensity of light emerging from filter B. So it has been rotated to filter B, but after it has been rotated, the intensity of light emerging from it, from filter B, is 1/4 I naught. Remember, I naught was the intensity we're entering filter B. Remember, this intensity was the intensity of the vertically polarized light that had passed through filter A. So the vertically polarized light that had passed through filter A, when it comes out of filter A, it was now vertically polarized. When it enters through filter B which has been rotated, then it exits on the other side here with an intensity of 1/4 I naught. With an intensity of 1/4 I naught. After entering with an intensity of I naught on the other side. So then calculate the angle of rotation of filter B from its starting position. So now the question is asking us, calculate the angle of rotation of filter B from its starting position. We want to know how is the filter B, how far, how long has the filter B rotated from its starting position, such that the intensity that it is producing is 1/4 I naught. So that's what we want to know. If it is producing 1/4 I naught as the output intensity, the intensity which entered was I naught. Through what angle has it undergone? Remember, the light that was entering through it was vertically plane polarized, and the transmission axis of this filter was already horizontal, meaning that originally, the expectation originally was that none of the incident intensity I naught would enter at first. Zero of it would exit here. The intensity exiting here was supposed to be zero if it was not rotated. So if it is rotated now, such that now the intensity exiting is 1/4 of the original intensity, then the question becomes, through what angle has it been rotated? So then, to make this question, then we take the formula, Malus law. We say I, being the intensity that is transmitted, this is the incident intensity, cos squared theta. Theta represents the angle between the vertical and the transmission axis of the filter B. The angle between the vertically plane polarized light, I naught, before it enters filter B. The angle it makes. So if this is the vertical which we're talking about, vertically plane polarized light, and then the transmission axis of filter B originally is like that. That's what we have at first. So the transmission axis and the vertical was making an angle of 90 at first. So the question is, what happened next? What happened was that it was rotated, this filter, in this direction, so that the transmission axis is rotated in that direction. So we want to find the angle through which it has been rotated. But however, Malus law is not worried about that. Malus law simply tells us the angle between the transmission axis in green here and the plane of the polarized light, which is in blue there. That's what Malus law cares about. So theta is simply that angle. So Malus law does not care. So we just want first and foremost to find the angle theta, which is causing an intensity, output intensity of what? 1/4 I naught. So we then come here and then say the output intensity is 1/4 I naught. The input is I naught. Then we divide both sides. I naught and I naught cancels. We are left with cos squared theta is equals to 1/4. Then we find the square root of that. We find the square root. The square root of cos theta is equals to half. Having found half, then we say inverse cos of half, we get 60. But we don't just end at 60 now. Because saying theta is 60 would imply that we have rotated the filter in the opposite direction. Because originally, this is the transmission, this is the plane of the polarization of the light, which is entering the filter. And the filter is like that. So originally, the angle theta here is equals to 90. So if you are going to rotate it like this, what can only happen is that the angle theta can only increase from 90. It cannot be 60, the angle theta, unless maybe we rotate it so much that we come to this other side again. But as a start, the angle theta cannot be less than 90 because it's already 90. So us increasing that angle or rotating again is simply increasing the angle theta. So we know also that to get half, if you say cos theta, you get half, you can also use 120. Cos of 120 can give us also half. But we have to be careful now here for this one. Why? Because 120 gives us minus half. So where am I getting minus half? Because here when I said square root of 1/4, I also got minus half. It was plus or minus half. So it was either cos theta was half or cos theta was minus half. So inverse cos of minus half gives us 120. Inverse cos of minus half again gives us 240. And inverse cos of half gives us 300. So 300, if you say cos 300, you can get half. Cos 240, you can get minus half. Cos 120, you can get minus half. So these are possible angles of rotation which can give us the 1/4 which we want there. 1/4 of the intensity, so that we are left with 1/4 of the intensity that entered. These are possible angles of rotation. These are possible values of theta. So if these are the possible values of theta, the question is asking us, calculate the angle of rotation of filter B from the starting position. So if we are looking for its rotation from the starting position, if we know that the angle which is causing an intensity of 1/4 the original intensity to be 120, but we want to know its angle of rotation from the starting position, and the starting position theta was already 90, then we then say 120 minus 90, or 240 minus 90, or 300 minus 90. You get it? So, and it doesn't just end here. That's why we have the other angle as 330 there, because we ended here. But otherwise, there is also another angle here afterwards, which we did not subtract. There's also another angle in the sense that in as much as we could have, it is much possible also that we could have rotated to come back here where we started again, or to come back to some point where we started here again. Remember, we started here. So to start here, we can go right round, to come maybe to a bigger angle, slightly bigger than that. Because remember, we know that secant will cause that. But secant to cause that, then it means that we have to have rotated an angle. For the angle here to be 60, it means that we would have started from here and rotated such that we pass by here again, such that we leave and open up an angle of 60 there. So to open up an angle of 60 there, the question is how much will we have rotated? We would have to rotate to somewhere, this point, such that there is still 90 here. You get it? So the question is how much of a rotation is that one from the original rotation? If we started the rotation from here, we would have to go right round and come somewhere here. So the question is how much have we rotated? So it's better to say 60 plus. So that is that in that case, as you can see, that's another one also. So in which case you must understand that that would be probably 450 as an angle because we have passed by 360, so we would have rotated an angle of 450. And then we say 450 minus 90 also. Okay, that is fine. So this produces these angles here, and this one here, this one here, this one here, when you subtract 90 from those angles to see the angle of rotation. Then next, a microwave of intensity I0 and amplitude A0 meets another microwave of the same frequency. So we have a microwave of intensity I0 and amplitude A0. It meets another microwave of the same frequency and of intensity 1/4 I0, traveling in the opposite direction. Both microwaves are vertically plane polarized and superposed when they meet, meaning that their displacements add when they meet, algebraically, of course. Explain without calculation why these waves cannot form a stationary wave with zero amplitude at its nodes. Now, the whole point is this one. Already these waves are satisfying two conditions that are needed for stationary waves. They are traveling in opposite direction, they have the same frequency. So they are both microwaves. So the general feeling was that they should be able to form what? A stationary wave. But they will not form a stationary wave with the nodes, with zero amplitude at its nodes. It is for the same reason that they have got different amplitudes. How do we know? We know this from this logic, that intensity is proportional to amplitude squared. So this one has an intensity of 1/4 I0, the other one is an intensity of I0. So they cannot be having the same intensity, amplitude, sorry. So if they don't have the same amplitude, it means that when they meet, they are never going to have a situation. There might be situations, of course, whereby they cancel out the displacements to give us zero. But it is never going to be permanent like that, because there's always a situation whereby at some point, that point where we expect that the displacement will be permanently zero, sometimes it will never be permanently zero because there will be no continuous cancellation which gives us a consistent zero because the amplitudes are different. So if you want to have a stationary wave with nodes where there is permanently zero amplitude, we must have waves which are meeting, which have got equal amplitudes and also are traveling in opposite direction and have a single frequency. So the only problem here is that they did not have equal amplitude. So they have different amplitudes. So they can never have a resultant displacement that is always zero. Then the next one asks you, determine in terms of amplitude the maximum amplitude of the wave formed. So the maximum amplitude of the wave formed happens when these two waves meet, maybe crest and crest. Obviously, the other one is a small amplitude, the other one is a big amplitude. So when the crest and the crest meet, or trough and trough meet, then that's when you are going to have the maximum amplitude. So we need to know, of course, for the other one with an intensity of 1/4 I0, what is its amplitude with respect to the other one which has got an intensity of I0 and an amplitude of A0. So to know that, we start with the equation of intensity. Intensity is proportional to amplitude squared. So intensity is equal to Ka squared. So for that one with an intensity of I0, we can say that it also has an amplitude A0. So we can substitute it into this equation and we get I0 is equal to Ka0 squared. So then we divide I and I0. Why are we dividing like this? Because we are saying that we want to look for the amplitude. We want to look for the amplitude of the one with an intensity of 1/4, with an intensity of 1/4 I0. We want to look for its amplitude. So to look for its amplitude now, we divide both sides. We say, okay, let's divide here this I and this I0. So that will be the same as dividing this side and this side. So once we do that one, then where there is I, we now put 1/4 I0. We are looking for its amplitude. So I0 and I0 cancels. Then if I square root both sides, this 1/4 is square rooted and I'm left with half. So A over A0 is half. So A, if I multiply both sides by A0, is equal to 0.5 A0. So in other words, the amplitude of the wave with the intensity 1/4 I0 is equals to 0.5 A naught. So this one is an amplitude of 0.5 A naught, whereas this one is an amplitude of A naught. So if you want to find the maximum amplitude of the wave formed, it will be adding this respective amplitude, A naught plus 0.5 A naught, to give us 1.5 A naught. So our answer is 1.5 A naught, like that.